Thank you very much. So welcome to my second talk on this conference. Today I will present a work that started when we, started to work on power management in data center, okay? And the idea is, as you know, data centers are increasingly important today because you don't have only data center for big IT services, but you have data center inside the cities. So urban data centers are not so well designed as, let's say, only Google and Amazon can do. Urban data centers are deployed in, let's say, pre-existing buildings that are not optimized for heat, climatization, and so on. As you know, so monitoring the heat dissipation in data center is very important. It's very important because, roughly speaking, you know that half of the energy used in a data center is wasted for climatization of the room, so heat and ventilation. And also, frankly speaking, let's say, only less than 1% of the energy of the fuel sources that you burn are used for effective computation on CPUs, okay? All the other energy is spent for IT equipment, more or less half of the energy that arrives to the building, and so other equipments that must be monitored and are auxiliary equipment, but only less 1% are used for computational processing. So it is very important to have a big picture or a clear picture about what happened in the data center. And the idea is to monitor not only the CPUs and the data center itself, but all the auxiliary equipment like PMUs, PDUs, storage racks, and so on. And the idea is to use a pervasive use of monitoring system that can be connected direct to the board, but usually you don't have a direct power supply line in some of the IT equipment. So you have to use a temperature and other kind of sensor that must be, let's say, energy harvested equipped, so it must be self-powered. So the idea is to design an Heatsink that is just not an Heatsink for processors, but it is an Heatsink that can measure temperature and other environmental quantities using the heat source that is dissipated by the IT equipment in a data center. So you have a board with a TIG generator, so a thermal generator with all the electronics on board to make processing, acquisition of the sensing quantities that you want and sending this sensing quantity. Of course, since you have intelligence on these Heatsinks, you can use this intelligence also to add some additional feature to the data center itself, so to improve the efficiency of the data center. So you can use this energy that you acquired using the heat dissipation just to help the processor to have a computing burst, okay? Or use this system as an infrastructure in your data center that can be used to propagate other kind of data. So today I will not enter into detail of the first, that is computing burst that is for free, but the principle is very simple. You extract energy from the heat dissipation of the processor, and you have to know that in a data center, of course, you have thousands or millions of this processor. You extract energy, you convert this energy, and if you don't want to use it for other kind of sensitive processing, you can, let's say, inject later this kind of energy using a fan, so you enable an active cooling, and so you can guarantee an active computational boost to your processor because you decrease the temperature on the processor, and so you can guarantee some more minutes of high intensive processing on the machine. The second path is use this kind of Heatsinks as a temperature sensor, okay? So what I present today is a kind of this system. So you have a TIG generator, you have a DC-DC booster, you have a local storages that can be a supercap or other kind of storages of energy, and you have a simple mechanism that can trigger a sensor node where you can acquire the temperature or other kind of, let's say, important information like the power consumption or the electrical consumption of your racks. You have to know that a racks usually has 100, 120 different power lines, okay? that you have to measure in order to see what is the power consumption of your rack. So this is the system, and we have characterized this system. So this Heatsinks is on the top of the processing microprocessor and power a simple sensor node. And according to the activity of the processor, in this picture we have just run a benchmark that is a video encoding of MPEG content, okay? And you can collect different amount of power, okay? In the order of quite a milliwatt or half a milliwatt. That is much more than enough to use and to power this sensor node. Of course, we have characterized several configurations from the, let's say, each generator. We use different kind of microprocessors that are normally used in data centers. They are ARM class processor, and you have to know that is a big trend towards the microservers that use ARM architecture instead of complex architecture, and different kind of, let's say, thermal electric generator, okay? We use some commercial devices and also some, let's say, prototypes that we build in our lab. And we compare the maximum efficiency comparison to the benchmark that is executed on the processor and the amount of energy that you can get from the thermoelectric generator. We also, let's say, tested the thermal stability of the system, of course, because since you are performing some computation on the microprocessor, if the microprocessor is without any Heatsinks, of course, at the full load and the full frequency, you get very, very quick the maximum temperature range. Then an internal power management guard will decrease the frequency of the processor itself, just for safety of the processor itself. So you cannot continue with the maximum computing capability. If you use a normal Heatsinks, you have the temperature controller in a specific range, and if you use this kind of generator, you have the same temperature controller in a specific range that is much more sustainable for the processor. So you don't have some kind of thermal problem about dissipation of this thermoelectric generator and the Heatsink. Then we characterized the different temperature gradient between the surface of the microprocessor and the temperature in air and the amount of power that we can collect, okay? It is a different picture. In the first picture we have seen, let's say, the normal benchmark. Now we have the delta between the surface of the chip and the air, okay? And we modeled, acquiring a lot of measurement point, a possible curve about of the systems that we have selected. And we experimented what is the minimum sending rate that you can achieve completely batteryless, okay? So the idea is, in this picture, you have different operating frequency of the bigger processor, okay? And different workload on the CPU, okay? You can have a CPU that run at high full speed, but it is under, let's say, underutilized, or you can have the same processor at the full frequency and with 100% of utilization. Of course, this difference can create different thermal gradient between the two surfaces, and you can collect different amount of power that can be used later. Of course, higher the frequency and higher the utilization, you can collect a lot of, let's say, a lot of power, and so you can permit a very high rate of sending packet with your sensor node. With less frequency or underutilization of the processor, the energy that you can harvest is not so much, so you can have you have to wait enough time to collect energy to send the packet with your sensor node. This can be seen also in this sustainability curve, where you have the delta gradient of temperature between the two surfaces and two regions. The green region is the region where you have the full sustainability, okay? And on X, it means that with such kind of temperature, any packet that is sent with this interval rate can be fully autonomous. So you collect enough energy to process and send the packet. Of course, if you ask a much more reactive system, let's say that you ask to send a packet every minute or even less, of course, this balance between the energy that you get and the energy that you spend is not positive, and you have to add additional energy source, for example, battery or an external power supply. Okay, so more or less I have complete my presentation. I've seen that it is possible to extract energy from the heat dissipation of processor in data center or any kind of high performance computing. You have to think that this system can scale, okay, because you have a lot of processor in the data center and in a single rack and in a single server, and you can scale this also with all these devices that you have, because the idea is to embed electronics and the capability to process directly inside the heatsink, okay? So you have an infrastructure on the top of your high-performance data center that can be used to extract information, temperature or other kind of information, and can be used to as an environmental monitoring system for your data center. The second part that I just started to announce is you can use also this extra energy that you can collect to improve the performance of the processors. Okay, more or less.